Any news from anybody else?
No.
Okay, maybe let me just see. Maybe they didn't get your mail.
Maybe they got my mail. Everybody got my mail. It's no more. It's not 1998 anymore. Everybody gets email now. It's delivered.
Okay. Yeah, no message.
All right. So Manu, how are you feeling today, and what is your desired takeaway?
I'm cool. I feel cool. And I want to take away as much as possible, just learn and grow. So that's it. Richard, how do you feel? What do you expect?
I'm feeling pretty good. We're coming out of a little bit of our minus 20-degree weather, and it was only minus 12 today, so that's a little bit refreshing. Uh, so that was good. Um, yeah. So um, and in this past few days, in terms of being able to meet with different people, I I've been in contact with somebody who has been working with international schools in Vietnam, and they've been doing some of our suicide prevention training work. So um, I was corresponding with her, and I was telling her that one of my basically a former student who was a Vietnamese sort of refugee back in the 70s is now a member of our faculty. And so I thought I was corresponding with a native Vietnamese person. And then she came back to me and said, actually, I'm from Ukraine. And I've been in Vietnam for over 10 years, working in this international school environment, which is somewhat similar, I think, to what Anne is doing. Um, and and so we've been in some really interesting exchanges in the last 2 or 3 days. So that's been great. So it's uh, it's always a real sort of delight to be able to connect with people in other parts of the world. And even though you can't have a physical sort of uh, in place kind of contact, it really broadens the opportunity to meet with other people and exchange ideas and dialogue with them. So yeah. So Fred, and how are you and feeling and your kind of expectations for today?
Thank you, Richard. Um, I'm feeling that minus 20 F is the best temperature in Fahrenheit because it's an easy translation to Celsius is equals to minus 20 Celsius. So
That's
minus,
right.
minus 20 F is a good one. Um, I'm feeling I'm feeling okay. I'm feeling okay. I'm feeling rested, which has not been the case for most of the week. For some reasons, I was tired. Uh, so it's good to feel rested. There's a sunshine, and I realized that the sunshine comes from my left over there, and my face is nearly half in the dark and half in the sun, and it fits very well with the sunshine uh, rising, passing through my background. So I think it's quite an interesting lighting there. My expectation is that no matter how many people show up, we're going to have a good call. So that's I expect to have a very good call today. Thank you. So how would you like to proceed? Should we go and read the cosmic railroad tracks, the great circles, and deprive the absence from Manu's insights about great circles? Or should we keep this for next week when more people will show up?
I think we should progress on with the great circles.
Okay, I was
Yeah.
expecting that from you.
No, I just think that,
No,
you know, we
no can resist the great circle. Okay, I'm going to share my book, if you would like that. So how do I do that? Bear with me a second. Months ago, I was quite fluent, but I've not done it in a while. Share. Share. There we go. And then I need to open my chat window. There we go. All right. Richard, are you okay with reading, or would you like me to do it? Or Manu, would you like to read? Who's going to read?
We can take
I can
turns.
start with the reading. So we're on
We've
chapter
got
14.
yes, we have page. Do you have the? Did I share my screen?
Yeah,
Oh, you have the book. Okay,
yeah.
it's
Well, I've
page
got both.
231. Lee, welcome aboard. How are you feeling, and what is your desired takeaway today?
Well, I am enjoying myself. I just came back from a nice Christmas dinner and music and all kinds of things. I really enjoyed it. Hold on. I got a tickle.
Mm-hmm.
I did not look at the book, so I have no idea what we're studying. But that sure looks like a Christmas ornament down there on the
Yeah.
page. So I'm excited to find out more and more. Railroad tracks, cosmic railroad tracks, like those. I can't wait. And who do I pass it to?
You pass it back to Richard, who's going to read. Thank you, Lee. We have not started. We're just about to start when you showed up.
Oh, wow. All right. I'm glad I wasn't too late. Well, Richard, how are you doing? And what are you wanting to get out of tonight?
Yeah, we've all gone, Lee, and so we're just starting into the reading, so I'll pick up from there.
Oh, all right. I'll get back to the readings.
So we start off with the any planar closed loop drawn on the surface of a sphere is necessarily a perfect circle as a result of the sphere's steady curvature. Such loops qualified as either great in quotations or lesser in quotation circles. And the distinction is defined in mathematics as follows. A great circle is formed by the intersection of a plane passing through the center of a sphere with the surface of that sphere. Any other circle, no matter what size, is lesser. The center of a great circle coincides with the sphere's center. In short, a great circle is an equator found in any angular orientation, but always around the fattest part of the sphere. What's so great about a great circle? Well, above all, it provides the shortest route between any 2 points on a sphere. This geometric fact is not obvious in many cases. For example, looking at a globe, it appears that the logical route between 2 points situated some distance apart on the Tropic of Cancer involves traveling along their shared lesser circle band in figure 14.1a. However, the principle is made more obvious by Fuller's juxtaposition of two extreme cases. He describes a small lesser circle near the North Pole of an imaginary globe and labels 2 points A and B, figure 14.1b. As with the larger Tropic of Cancer, the eye naturally travels from A to B along their mutual lesser circle path, without suspecting that this represents the long way round. Further, then redraws the same lesser circle in a new location, superimposed over the globe's equator, so that A and B both fall on the horizontal great circle. The shortest route between A and B is suddenly obvious. Likewise, between any 2 points on a sphere, the most expedient route will be a great circle segment. Fuller's example makes it easy to see that a lesser circle path will always present a detour. Other special circumstances, or characteristics, sorry. Any two great circles on a sphere must intersect twice, specifically at 2 points, 180 degrees apart. There's no other possibility unless they are actually the same circle. Two great circles can neither avoid each other altogether, nor intersect only once, nor intersect more than twice. Finally, the junction of two great circles inscribes two pairs of equal and opposite angles on the sphere's surface, whose two angular values add up to 180 degrees. The statement is equivalent for the intersection of two Euclidean straight lines. Lesser circles do not share this property. In fact, their intersection produces opposite angles, which are necessarily unequal. In conclusion, on the surface of a sphere, only great circles have the geometric characteristics of straight lines. As we examine different aspects of great circles, you will notice that much of this material is quite complicated. The patterns are too intricate to be readily visualized in the mind's eye. Furthermore, connections drawn between the geometric models and the physical phenomena are usually speculative. However, as Fuller Synergetics devotes considerable attention to great circles, anyone who has tried to decipher these sections will welcome full coverage. Referring back and forth from the text to the drawings will be essential.
Maybe we discuss a little bit what's been said there. Anybody has something to say?
It's just full of definition. It's full of definitions, that's all. We have to understand those definitions properly. And that's it.
Well, sort of an extension of this too, for me, has to do with the Dymaxion map that comes out of this particular kind of great circle discussion, and how accurate it is in terms of being able to tell the directions that you're going. And I had some kind of fun with this when I had a position in Bombay, India in the 90s. And at times it was interesting to try and explain to people, where I came from on Earth. And what we figured out, because Bombay and Calgary are sort of about halfway around the Earth from each other. Time-wise, we're about 12, maybe 12 and a half hours different. So when you looked at the Dymaxion map, what I discovered, of course, was an opportunity to ask students, how do you get, what directions to go to get from Bombay to Calgary and from Calgary to Bombay? And as it turns out, when you see it on the map, and it's sort of the Great Circle approach, but you fly north from Bombay to the North Pole, and then you fly south to Calgary. And if you're going to Calgary to Bombay, you do the same thing. You fly north from Calgary and then south to Bombay. So you go the same way both ways. And I think this great circle kind of discussion helps to appreciate what the world looks like on a flat map when you use the Dymaxion approach that Fuller did.
Okay. Can you still do that these days with Russia's airspace close to Western flights in response to?
Well, no, it
Western
was
flights
only
to-
it was only like kind of a metaphor. It was like if you could fly like the crow.
Yeah. I know. I was just thinking about that because a lot of things have been disturbed by Europe's decision
Yeah.
to prevent Russian to fly over Europe airspace, which was followed by the retaliation that Europe airlines cannot fly over Russia, which was followed by US retaliation that they would prevent their own flights from flying over Russia and prevent Russian flights from flying directly to the US. So this has made long travel by airplane a little bit difficult. And now Japan is cutting itself out because Japan has followed Europe and prevented its airlines to fly over Russia. And now Japan is getting into a fight with China. But if China takes the decision to prevent Japan's flights to fly over its territory, Japan is completely isolated. They need they won't have any direct flights from Europe. Going from Europe to Japan will take stops over Dubai or Singapore or stuff like this. That's
Fred, do you believe any politician even understand this thing?
I'm sorry?
Do you think that any politician understand this stuff? They have zero understanding of what we just read.
They don't understand it, but
Yeah.
they understand 36 hours on a flight compared to 12 and a half hours.
Yeah.
Yeah, but even that is completely not, is a little bit nutty because 36 hours you're burning fuel. Whatever you do,
Yes.
you're burning fuel.
You're burning fuel. Right.
So metaphorically, it is the same thing as traveling on a lesser circle. Because the great thing about great circle is that you are traveling along, if you want, in the plainest of the hypotenuse between 2 points. That's all. Because there's one point that is the referential, that is the center of a globe, and then any 2 points, you are trying to travel along the hypotenuse of the whatever triangle. So it is by definition the shortest.
It is by definition the what? The shortest. Thank you.
Shortest.
Shortest. Thank you. Yes.
Sure.
Yes. Okay. And there's one thing about lesser circles, even great circles, that when you trace a circle on a sphere, where's in and where's out? So you have so you've just created a boundary on a surface, on a finite surface, that doesn't define an in and an out. It's just define two partitions. And if you want to call them in and out, it's just arbitrary. There's no in and no out anymore.
Okay, if you want to get into that, the circle doesn't exist, actually. So let's not go there.
It's amazing how close to what my father, as a pilot all of his life, and flying the P-47 in World War II, and then he even flew the biplane and then he joined United Airlines and flew all the way to Japan and back again to Denver. And yes, the shortest distance to Japan was over the Arctic and on the north end, and it saved time, gallons and gallons of fuel.
Okay.
It's amazing at being able to do that. And I would have thought it would be more difficult just because you're going up and over. As a child, I thought that. But of course, I'm seeing a whole different picture now of that. And I enjoy reminiscing today with my father. And he says the only way we go is over the Arctic.
Mm.
Thank you for
I
that.
was going to say something in anticipation, but we're going to get there. I think that I'll make the comments when we reach it.
Okay.
But it's a general stuff that flows from the principle. Maybe I'll say it now. We not mean
Maybe hold on to the thought first. I have something to say in response to Lise, if you allow me. When you fly from Beijing to New York, the flight is shorter over the Arctic than when you fly from Beijing to LA.
Mm.
And when you look at the map at a sphere,
Uh-huh.
New York is on the other side.
Yeah.
And LA is just across the ocean. So intuitively, you think LA would be a shorter flight, but no. And in order to fly to LA, you don't fly across the ocean. You fly all the way
up
to the south of Siberia and all the way to Alaska, and then south to LA, following the California coast and all that.
It's amazing.
And when you fly to New York, it's straight over the Arctic, just like you explained for Japan. That's all I wanted to say. Manu, go ahead.
Okay, there are two things about great circles that are very important. We know that everything that we talk about is about what Steve would call fractals. You have system repeating in the fold and unfold. So they repeat the symmetry. The principal symmetry here is that you are using the center of the globe. If you are using the center of a globe, that is a fractal of something that is bigger, because the centers are also in symmetry in relationship to the global cosmos. That's the first thing. The second thing is that the principle is energy flows. The first principle is everything is energy. Energy flows. Energy always flows. Energy flows to the line of least resistance. So if energy has the same power, and we know that work is power times the distance traveled. That's the definition of work. So, or the time travel, whatever. So if work is that way, the line of least resistance for the flow of energy will be the shortest between 2 points. Therefore, energy is going to flow along an arc of a great circle. And more so, electrical energy. I always hold that electricity flows along edges of structures. Whereas magnetism flows along windows, across windows. Okay, those were the 2 points that I wanted to say in support of the importance of the great circles.
Thank you. Thank you. This triggers a lot of things in my mind. One of those things is a physics experiment. No, not an experiment, the physics, let's say, exercise given to undergraduates, which is you take a Earth and you imagine a tunnel straight through the center, or straight through directly between 2 points on the surface of the Earth. And if you drop something through that tunnel, which goes straight to the point you want to go, it first accelerates under the action of gravity, and then it decelerates and arrives at its destination point. So you could,
Yes.
if you had such a tunnel, you could jump through it and do a backflip in the middle in order not to land on your head, and then suddenly get out of the hole and land at you could do that. So, and the travel time is extremely fast. I forgot but it's like it's like a few hours just to go through because of gravity. You got acceleration for the first part and then deceleration on the way out. I thought that was a very interesting exercise to think about this mode of travel. Anyway, that was more anecdotal. Shall we keep going? Is there something more to add?
Yes.
Richard, you okay to keep going, or you want to swap somebody else?
Well, I can go a little bit more, sure.
Okay, thank you.
Why are we talking about spheres? That's my question to Manu. No. The vertices of regular and semi-regular polyhedra lie on the surface of an imaginary sphere, which is to say that all vertices are equidistant from the polyhedron's center. Given this fact, we can picture spherical versions of each polyhedron, in which the polyhedral edges have stretched outward to become great circle arcs, and the faces have expanded into curved surfaces, as if each shape has been blown up like a balloon. 14.2. Right, yeah. 14.2 shows a spherical tetrahedron, octahedron, and icosahedron as examples. Comparing these systems with their planar counterparts, it is clear that the polyhedral edges are actually chords of great circle arcs. We conclude that the shortest distance between two events of a system always involves a great circle. The concept, rather than the reality, of a sphere, i.e., an omnisymmetrical container, acts as a frame of reference for polyhedral systems. Spherical polyhedral thus introduce new versions of familiar characters. The topological information, that is, the numbers and valences of vertices, edges, and faces of any polyhedron, are displayed on a spherical canvas. An obvious consequence of this type of display is that the shape is no longer a variable. Shape similarities, which are so rigorously accounted for by A and B modules, are thus ignored. Our investigation now focuses in on the topological or surface characteristics. Transforming polyhedra into balloons temporarily equalizes shape and size, providing a common denominator for other comparisons. This process develops a somewhat unorthodox chart. So I always liked this particular part because it really helps one understand what happens when you push the edges of a straight edge, like a tetrahedron, out into a curve or an arc to give you a full circle, or in the tetrahedron model, you get a full sphere. And I always remember Fuller at one point saying that how did he say it? It was a circle is really just a great triangle. And you could probably argue that it's a great arc or a great circle triangle. So I'll go on then to the new classification system. However, the chart is not yet complete. Simply projecting edges and faces onto a spherical surface does not teach us anything new. We have yet to exploit the nature of the sphere. Spheres suggest spin. That's how synergetics initially arrives at the omnidirectional form. Spin any system in all directions, and ultimately the action will have defined a circumscribing spherical envelope. Fuller places considerable emphasis on the spinability of systems, arguing that as everything in the universe is in motion, the different axes of spin inherent in systems are worthy of investigation. All polyhedra have three sets of topological aspects: vertices, edges, and faces. These sets correspond to the three types of axes of a rotational symmetry or spin, which connects pairs of either polar opposite vertices, mid-edge points, or face centers. As a polyhedron spins about any one of these axes, an implied great circle is generated midway between the two poles, in other words, at the equator. Equators corresponding to all existing axes of symmetry can be simultaneously represented on a spherical surface, creating an exhaustive chart of the topological symmetries of a given system. Each symmetrical polyhedron has its own great circle diagram, which incorporates all its axes of rotational symmetry or axes of spin in Fuller's terminology. The patterns generated by related polyhedra may include some of the same circles as determined by common symmetries. However, the complete chart of a polyhedron is exactly shared only by its dual, as it will be shown below. Great circles reveal a new aspect of polyhedral intertransformability. A novel, if obscure, means means of detecting symmetrical relationships among systems. We can anticipate the emergence of decidedly unfamiliar patterns in this game, for their resemblance to the source polyhedron is sometimes subtle. Finally, in pursuing this study, we discover new variations on upper limits and minimum cases. Great circles thus provide another tool with which to detect inherent spatial constraints.
Can we comment?
Yeah.
Anybody notice something in relationship to spin?
What do you mean?
Okay, did you notice the subtle reference to poles?
What?
The subtle reference to poles, that is fixed. If you have a spin, it necessarily means that you have poles.
Right.
You cannot spin without poles. Impossible. If you read at the top of page 234, all polyhedra have three sets of topological aspects: vertices, edges, and faces. Okay. The set correspond to the three types of axes, rotational symmetry or spin, which connect pairs of either polar opposite vertices. So you cannot have a spin of anything. You cannot turn anything without having poles. These two must be fixed for you to be able to spin, to define the spin. In other words, you cannot have a circle without the axis that is perpendicular to the surface of a circle. Okay. That is the first subtlety. And then the second thing is here.
Objection. You can have circles.
Okay.
You can have circles without knowing the center. Therefore, you
But
can
if
have
you don't know the circle, it doesn't mean that it doesn't exist.
Mm.
Not knowing me, having
No,
circle,
no.
not knowing.
You said you cannot have a circle without its axis.
Yes.
Well, you can.
How?
Well, you can have a circle without an axis.
How? Tell
If
me.
you don't know the circle
I
center,
say a spin. You cannot have a spin
okay,
without an
spin.
axis.
Okay, so you misspoke. That's okay. Then
Yeah.
we
She defined a circle as the track of a spin at equal distance from a center. That
Yes.
is the definition that we have here.
That's one way to define a circle. Yeah.
In the way to define it.
Okay.
In a tactile way. In a
It's fine.
tactile way, as you
It's
like to
fine.
say.
It's fine. You just misspoke, and now that you corrected it, we're in agreement. Thank you.
Okay, good. All right. But the point that I wanted to say is that you come in here to Euler's identity, because Euler identity is typically topological. You have vertices, faces, and edges. And people they don't understand what is the two that exists in that system. The two is the poles, the two poles of opposite direction. That is what represents the two. So topologically, Euler identity is the relationship between vertices, edges, faces, and poles. The four of them form a system. And the system is what it is.
Why do you say topology? Sorry,
Pardon?
Richard.
Sorry,
Richard.
Oh, sorry. Yeah.
No, go ahead. You go ahead, Richard.
What I was just, again, these are playing on words, but to say that those four form a system, and then what I would want to come back in dialogue with is what kind of system, and that's when you get back to the understanding of a tetrahedron as being a minimum whole system. So it's also something that we skip over at times when we're trying to understand why four is so important in the sense of the tetrahedron being the minimum sort of whole system or the minimum sort of coordinate system of universe. Does that make sense?
No, it is. It is. But this is more general than the structure. It holds of anything. Anything. It's like any set that you define in that way will form something.
Yeah, it's the minimum of forming. It's the minimum form of something.
Yeah.
Yeah.
It is like we're talking about the phi, the pi, and the thing. So you have the phi that is like this, the pi like that is like that, open, and then you have the in between the two. Or you have the filtration and then the repulsion. It forms a force something. I'm just talking about more general. The phi is what protects the dampener or whatever is aggressive that is coming onto wherever. The pi defines that convexity that repulses. And then you have the function of the two, that is to let in or to repulse. Those three form four. And you might say that the boundary as defined by phi and pi are the poles. You can say so.
Yeah. No, what my point is, Manu, is that it has to do, in my mind, with the classification system. And when I first understood or was taught something about systems and the excitement around systems when you read the definition of a system, it said it was a set of interacting parts. And at some point, I started to be cheeky, maybe, as a student. And I said, so how many parts does it take to make a system? And nobody would answer or could answer. Or they just gave me a brush-off answer of saying, I don't know, 2. And
Great.
no, what I'm trying to get at is they would not give me any answer along that line. And it was until I read Fuller and he set forward the definition of a minimum whole system has to have 4. That's when I said, well, he's the definite about the answer to my question. And at that point, I couldn't care less whether he was right or wrong. I was just happy that I got an actual answer, a concrete, if you want, like that kind of answer.
Yeah. But Fuller say it quite actually explicitly. He say a minimum system is 3. It is input out. Yes, it's an input output box. You say input, a box, and output. That is 3. And then when
just hang on. Yes, let's follow that, because the minimum system is 3. The minimum whole system is 4.
Is 4. Exactly.
And that's in the language of just trying to teach it to somebody else. We sometimes slide over the language of minimum system is one thing. Minimum whole system is something slightly different. And
actually, very different. Very different.
Yes, right.
Because the whole system implies feedback
but
loop.
Similar in the sense it's only one additional point.
Yes, yes.
But as you say, when you dig into it, it's a huge difference between 3 and 4.
Yes. And go and explain to anybody that is 1 kink more. Just 1 kink more. Because if you talk about the system as input, output with a box in the middle, that can go anywhere. But the moment at the output, you imply a breaking, a kink, that is an additional point, there's a possibility of a feedback. Because the kink is going to go around. So go and explain that to somebody that feedback loop is actually just 1 event. That is the kink. To make it 4.
Well, and that the other, I think this parallels, but this goes back to Fuller as a student, as a young student, and the teacher saying, when you draw the chalk line along the blackboard, it goes out to sort of infinity. And Fuller was sort of saying, no, I don't think it does. And what he was getting at was is that it goes out to the edge of the blackboard, and then it kinks, if you want, down the edge and back around the back, and then comes back up and connects where it started from.
Yes.
And I think he got thrown out of class even as a grade 2 or grade 3 sort of observer of this phenomena.
Which is interestingly in what sort of geometry? In projective geometry. In projective geometry, that's the definition of the point at infinity. The point at infinity, there's only 1 point at infinity, which is a circle around the space, which is quite an interesting concept. And this concept of point at infinity is what ties up the whole idea of projective geometry together. Thank you. Thank you for that.
Yeah, thank you.
And we should know that kinks exist, But the circle is idealistic. The king exists. We can make a king because we can structure it. We can make kings finer and finer and finer to approach the circle. That's where the phi come from. We make kings, 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 kings. We define a series, finer and finer and finer, hoping to get to the smoothness of a circle, but never actually going there. We're getting into a golden ratio of our curvature. That's what it is. That's, feeling as we want to do. That's what we are trying to do. It's like giving a kid small sticks, matchstick, and say, cut them and put them in such a way that they become the finest possible, the smallest possible around, and then they align smoothly. They will do it. The smarter kid will reach another level, but that is just an approach, a structural approach to it. And you realize that you can only do it from the inside to build it that way. You can only, in the house, put in it like that. There is something, in order to put it from outside, you really need to transgress that boundary of a house, go out and put the roof on. Anyway, this was another, just aside, it's not essential.
Thank you. Are you complete, Richard, with your question?
Yeah.
Okay. Manu, my question was, as we were talking about circles and spheres, why did you start your explanation with topologically, knowing that topology doesn't hold shapes?
In the beginning, there was nothing. And everything appeared with a word.
Yes, but it's not the starting point. Your starting point was topologically, and we were talking about shapes. So why is it you thought that was relevant? I want to know what you're thinking there.
Because of this thing here, let's say transforming polyhedra into balloon temporarily equalize shape and side, providing a common denominator for other comparison. So it expands your starting point. If I started with saying it's a tetrahedron, I will be limiting myself.
Yes, but why is it topological?
Okay, let me give another answer.
Okay.
And that one is that whatever we do, whatever sophistication that we have, we actually always comparing forms.
Comparing forms?
Forms, yes.
As in shapes?
Shape, yes. That's all we can do. That's the only thing.
Topology abstracts shape.
Yes,
it
that's what I'm saying.
Abstracts in the sense that it removes the notion of shape from any reasoning.
Well, but then
it describes properties which have no relationship with shape.
But you must agree with me that it expands your set of relationship then.
It has
if shape is no, it expands your sense of relationship, your set of relationship, in that if shape is no more a limiting factor in relationship, you can invoke a relationship between things.
Yeah,
that are just anything.
Yes. No, I understand.
I
understand what topology is used for and how it's used. But
yes.
Okay.
Why? The why. So my point was that it comes to the fact that everything is energy, and energy is always flowing.
Okay.
And the study of energy, in actual fact, the capability of perceiving those subtleties of energy that is always flowing is always the same thing that is being capricious. in all of the caprices. What is this caprice? What is that one? You need to be able to see it.
Okay.
I can see the horizon behind you as just a coloring of a little kid. But I can see it as a tapestry of universe, which it is. Or I can see it or a landscape of a highway, what you have behind you. Or I can see it as Fred, just Fred. Or I can see that I just reached it. So it makes that view, that plasticity of approach make our description, in my opinion, much more richer, not by degrees, but by powers, exponentially, much more richer.
Okay. Thank you.
Just to tap into that a bit, which is what I was talking about a bit at the beginning, in relation to a discussion we had today on another group. And I was raising the question of if everything is something other than physical, and in this case, energy, other words that were being used today is consciousness and yeah, energy and consciousness were the two main ones. And so I was raising the question around why do we then use the language of physical as if it's the starting place, and then beyond physical is metaphysical, and meta as a prefix means beyond. So out of these conversations, and especially what Manu has often talked about, energy is sort of the starting place. To talk about energy and meta energy would be physical. And so we get anchored to a particular kind of starting point rather than trying to work from a starting point that somebody else has if you want, defined in another time or another era. But we stay with that, even though when we say we're trying to get beyond it, or we're trying to be more inclusive of other things other than physical. Anyway, that just was part of the discussion, and when Manu talks about energy, I want to talk about energy, and then when we talk about the physical manifestation that can come out of that, I want to talk about meta energy equals physical.
Yeah. To me, Richard, physical manifestation is only the recognition of the observer. It's to say, in this vastness, I see you. So if I see you, yes, because Fuller says life starts with awareness of the otherness. So the moment,
not quite like that. It's in order for life to exist, there has to be awareness. In order for awareness to exist, there has to be otherness.
okay, yes, but they put it like that in the popular stuff. Let's start with awareness. So to me, the physical, that is the start counting of something, is simply the recognition that you are, the recognition of the observer, because it is the observer that defines locality. And we say the physical only manifests locally. Physical is not universal. Physical is checky. It is point. The physical is not continuous. There's physical here, there's physical there. Yes, there's a relationship, but it is not in terms of physical, it's not continuous.
Yeah, but
So
that's my point, Manu, is that with that kind of understanding, we still use physical as the starting point, and everything sort of emanates off of that or comes back to that. So we're into this habit of saying physical and metaphysical. And I'm just playing with the idea that if it's something else like energy, then why don't we start with the word energy, and then meta energy would be this manifestation by the
yes,
observer,
yes,
etc. Yeah.
yes. Why don't you start by saying you are God? I'm not saying it in a way, because starting from the whole is saying that you are God. I understand that.
No.
All in.
Well,
No, I'm not saying that in any kind of. No, let me not take that example. But
no,
you start as a
no. It's
you
a good
start as a whole.
example.
Yeah. You say you start like a whole, everything is energy, and it always flows. That's what it is. Meaning that everything is a whole, and there's always relationship. It always flows.
Yeah.
That's what it means. It's
Well, I think
restless.
the exciting thing about it for me when we say it's God, and if energy is the starting point, well, then that's sort of like saying God is energy. God isn't physical. And then when people talk about God out there and God in here is the same, and it now starts to remove the notion of God, A, as a physical being, and B, it removes God as a hierarchical being, and as an apex sort of being, and it makes this notion of God, however that is used, whether it's in one culture or another, that might be slightly different words that are used, but it means it's everywhere. it's the whole. Yeah, yeah.
You've got to. I mean, you have to start from there because nobody has ever defined energy other than to say it's a living thing. Energy is what it is. God is
Yeah.
what He is.
Yeah, well, that's like for me, I would also then say, well, then I go to meta energy, and meta energy may be a manifestation of something physical. If I treat God as energy, then meta God in my mind is a manifestation of something, and it happens to be human beings, let's say. And so we're a meta of energy, or a meta of that is.
Let me suggest something that might be of interest. We say every manifestation is a fractal of something that exists in principle. So God is the unity, the one. God is the one, the all and everything.
No, he can't be one in the sense of oneness. If the unity oneness definition is plural minimum two, then God has to be kind of in that as well, in that way. You can't just turn the God into a oneness by
Well, I mean, that is
itself.
oneness. I don't know how to define oneness emotion. So I don't know.
Anyway, I've taken us down a rabbit hole, maybe. So, but
Okay, well, Fred, you're very quiet.
Yes. And your point is?
So you have to give us direction. I mean, you have to give us the spin. Left or right spin. Which one do you give? So do we read or do we continue the comment?
I can give you silence so that we can so that we can ponder, reflect, and digest what's being said. It's been very profound.
Yes, that's another view that we locally we didn't see.
I'm a little bit puzzled that you say energy is not defined. Can you tell us more about that?
I don't know what I just feel energy. What is it?
Well, you can measure it.
I measure the effect of energy because I measure electrical energy, I measure magnetic energy, components of it. I don't measure everything. I cannot be something and measure it. I can only measure. It's like I see a person, Fred, wholly I see it. I can measure Fred's arms, height, things like that. But that's what I measure manifestation of energy. But I'm so used to it that I tend to say that manifestation of energy is energy.
That's the beginning of a definition. So energy is something you can measure by its effect, correct?
I wouldn't say that. I say I can. I'm inside, I can measure something, but I'm unable to say that that's something that I measure is a whole. I cannot say it.
Why not?
I can't say that all the things that I measure, when I add them up, give me a whole.
Yes.
I don't say that it's impossible. I say I'm unable at my current stage.
Okay, I'm not talking about you. I'm not pointing the finger at you here. But you can measure energy by its effect. Therefore,
yes.
If you see an effect, it tells you there's energy. If you see no effect, it tells you there's no energy. So you have found a way to identify whether there is or there is not.
But that what you say give the assumption that you are absolutely efficient. So the answer is no. It's the sensitivity.
Stop shaking the things to have wiggle rooms. Do we have a definition or not for energy? We do.
No, we don't have a definition.
It's something you can measure. If you can measure some effect, there is energy. If you cannot measure some effect, there is no energy that is measurable.
If I cannot measure, it most likely means it is sub or hyper the sensitivity of my instruments of measure.
Yeah.
I measure through.
Okay. Let's admit that this wiggle room means it's so small it doesn't exist. Yes?
I wouldn't jump there.
I'm sorry?
I will not say that.
Okay. So there's no definition for energy then?
For me, yes.
Okay.
Yeah.
That's fine. All right, let's keep going then. Bear with me, I'm sharing my document. Share. Click. Are you seeing the document?
Yes.
Yeah.
Okay, good. We are at great circles patterns. Is that correct?
Mm-hmm.
Okay, I will read. Great circle patterns. Let's begin with a representative system, the octahedron. We interconnect polar opposites, starting with vertices, followed by mid-edge point and finally face centers. 6 paired vertices are connected by 3 mutually perpendicular lines, the familiar XYZ axis meeting at the octahedral center of gravity. That's a figure underneath here.
14A, 14.3.
These axes define 3 orthogonal great circles which divide the sphere surface into 8 triangular areas, or octants. 3 symmetrically arranged great circles will always form the edges of a spherical octahedron. That much is straightforward. I give you a chance to stare at the diagram for a little bit. And I keep going. On 2 edges, the octahedron's 12 edges consist of 6 opposing pairs, the midpoints of which can be connected by 6 intersecting axes. The same number of great circles are thereby generated, delineating another facet of the octahedron's symmetry. Unlike the previous case, the pattern made by 6 great circles does not look like an octahedron. Its 25 right isosceles triangles outline the edge of both the spherical cube and rhombic dodecahedron, as well as the edges of 2 intersecting spherical tetrahedra, otherwise known as the star tetrahedron, thus highlighting the topological relationship between these 4 systems. This exercise demonstrates a new aspect of intertransformability. Great circles generated by a given polyhedron often delineate the spherical edges of its symmetrical cousins.
Or symmetrical derivative.
Finally, the centers of opposite faces are joined together. The octahedron's 4 pairs of triangles define 4 intersecting axes, and in turn 4 symmetrically arrayed great circles. As the spherical edges of Fuller's vector equilibrium, this pattern is particularly significant, as will be developed below. The sets of 3, 6, and 4 great circles can be all superimposed on one sphere to exhaustively display the unique topological aspects of the octahedron. With a grand total of 13, we have located all the great circles that correspond to the octahedron's symmetry. We can go no further. Now consider the cube. It is quickly apparent that its total great circle patterns will be identical to that of the octahedron. The cube's 8 vertices generate the same 4 great circles as the octahedron's faces. Its 6 faces correspond to the 3 orthogonal great circles, and the 12 edge midpoints are identically situated to those of the octahedron. Such is the result of duality. The same sets of circles are generated by different elements, and the end results are equivalent. Next, we turn to the vector equilibrium. With 2 kinds of faces, the situation might seem more complicated. However, the above procedure still applies. The vector equilibrium 8 triangle define the same 4 axes as the faces of the octahedron, while its squares contribute 3 orthogonal XYZ axes. 7 great circles altogether are generated by the axis of the 14 vector equilibrium faces. 12 vertices correspond to the same 6 great circles as those of the octahedron or cube edges. And finally, 24 edges spin out the unfamiliar pattern of 12 great circles. With a total of 25 great circles, the topological parameters of the vector equilibrium are exhausted. The tetrahedron presents a slightly different situation in that its vertices do not group into polar opposites, but rather are positioned directly across from the centers of faces. However, 4 axes of symmetry, all going through the center of gravity, can be created by connecting the vertices with their opposite faces.
Yeah.
In having axes of rotational symmetry that connects faces and vertices, the tetrahedron is again unique. As we recall from chapter 4, only tetrahedra have the same number of vertices as faces. Only the tetrahedron is its own dual. The 4 great circles generated by these unorthodox axes produce once again the spherical vector equilibrium. This is not surprising if we recall the lesson from multiplication by division, which first uncovered this shared symmetry between the tetrahedron, octahedron, and vector equilibrium. By simply interconnecting mid-edge points, all 3 polyhedra were found to be inherent in the topological makeup of the starting point tetrahedron. They share the same 4 axes of symmetry. The axes of symmetry associated with the tetrahedron's 6 edges are more orthodox. Mid-edge points of opposite edges are simply joined to re-establish the XYZ axis. Familiar by now with evidence of right angles hiding within this triangular shape, we can no longer be caught off guard by the discovery. These corresponding 3 great circles are the edges of the spherical octahedron, once again illustrating the depth of the octahedron-tetrahedron relationship. And now all topological aspects are used up. The tetrahedron has 7 great circles, the minimum number possible for symmetrical polyhedra. Next, we look at the maximum case. It's not easy to accept the concept of an upper limit on the number of symmetrically positioned great circles that can be imposed on a sphere. Common sense suggests that we should be able to keep adding new rings indefinitely. However, we recall from chapter 3 that all systems are polyhedral. That is, everything that divides inside from outside can be described in terms of some number, 4 or more, of event complexes and their relationships. And from chapter 4 that the system with the greatest number of identical regular polygons, and from chapter 4, the system with the greatest number of identical regular polygons and equivalent vertices is an icosahedron. This tells us that the number of great circles allowed by the topological aspect of the icosahedron is a maximum for these symmetrical patterns. The axis defined by the icosahedron's 12 vertices introduce 6 great circles. We already have a pattern with 6 circles, octahedron vector equilibrium that we just saw. However, this is an entirely new set, out of phase with the earlier group, as defined by the jitterbug transformation. Outlining 12 pentagons and 20 triangles, as opposed to 24 isosceles triangles, these arcs present the most symmetrical arrangement of 6 great circles. When a vector equilibrium contracts into an icosahedron in the jitterbug transformation, the radius edge length equivalent is lost, but the distances between adjacent vertices on the surface are suddenly all equal. As an icosahedron produces the most symmetrical distribution of 12 vertices on a closed system, it follows that the same is true for their corresponding 6 great circles.
I have a question.
Yes?
Now, is it saying that it has a jitterbug in that circle? I can't see how a circle can have a jitterbug.
No, it said the jitterbug transformation. Jitterbug
Transforming
transformation.
from where?
From one form to another. You know that the jitterbugs, Fuller goes from the vector equilibrium to the icosahedron to the octahedron
Oh, I
to
see.
the tetrahedron.
And it
The
doesn't
four,
say anything about the
yes, it just
circle.
goes, That's what you
Oh.
call intertransformability.
Oh, okay. Okay.
And
Now,
it does that by holding and twisting. It holds and it twists. That's what it does. It holds, holding, twisting, and pressing.
a circle?
Now it holds, imagine that this is a system. I hold it. Those are my poles. I twist it.
Yes, I
by
understand
pressing,
that, but in a circle.
by pressing. So these things start forming spirals that compress, and that goes through stable states.
But I'm talking about a circle having jitterbug. A circle wouldn't have it, not those many circles.
Okay, let me just see this one. This
Okay.
is something.
Yeah, I understand that one.
Yeah.
But not a circle. A circle doesn't jitterbug. It doesn't move. It can go around, but it can't go jitterbug side by side.
Okay. Do you see that this thing is an infinite number of circles within these 2 points that I'm holding? Circle, circle, circle.
Yeah.
Okay. If I twist it.
Oh, okay. Okay.
The circle are twisting. And they are compressing.
If it's in a lengthly instead of just a multiple of circles connecting together. Okay.
Yeah. In fact, it's saying that that's the way energy flows.
Oh, okay.
Energy always pulsates. It flows from stable to from unstable to stable, then unstable again.
Oh,
that's what it does.
Oh, okay.
Okay.
Thank you.
And anybody else?
Have you finished to the bottom of
no
of that paragraph?
No, I finished until
I'll suggest that you go.
I finished
you
until
continue
Lee,
to,
I finished until Lee said something. But while we are interrupted already, let's see if somebody has a comment.
I would prefer that we read to the as exposed below.
Yes, I heard.
And then we exchange how we understand this.
I will reread the last paragraph that mentioned the jitterbug.
Okay.
When a vector equilibrium contracts into an icosahedron in the jitterbug transformation, the radius edge length equivalence is lost, but the distances between adjacent vertices of the surface are suddenly all equal. As an icosahedron produces the most symmetrical distribution of 12 vertices on a closed system, it followed that the same is true for their corresponding 6 great circles. I don't know if that helps, Lee, but that's what
Well,
the last paragraph said.
6 great circles are a ball, not not what Manu was showing me. That was a narrow sphere or a tube. It's a sphere. They're talking about a sphere. Many circles.
Yes, basically what we're describing here are the great circles from various shapes that we've studied. And when you expand those shapes along those great circles, you create a sphere.
Yes. Yes.
Does that help?
Let's continue. Maybe it will come into.
Okay. Okay, I keep going then.
Can that sphere do a jitterbug? That one?
No,
14.
no, but we're not studying how a sphere can do a jitterbug. We're studying how the transformation of the jitterbug at different moments produces a sphere from the great circles.
Oh, I see.
And how this moves from one to the next and all that. So instead of looking at the jitterbug transforming only, we're looking at the great circles that can be drawn from the jitterbug and how this transform.
Aha. That makes sense.
Okay.
Okay.
Good. Thank you. Next, the axis of symmetry connecting the centers of icosahedron faces generates 10 great circles, while the 30 edges spin out 15 more. 6 plus 10 plus 15 equals 31 great circles. The total number of great circles in the limit case pattern is 31. These circles provide the spherical edges of a pentagonal dodecahedron, as well as those of an icosahedron, and less predictably also include the octahedron. These relationships will be explored below. And those 31 great circles are represented on figure 14.8. Least common denominator. The spherical icosahedron divides the surface of a sphere into the greatest number of completely regular domains, with both equal arc lengths and equal surface angles. We can therefore subdivide one of these symmetrical triangles to find the least common denominator of surface unity, in much the same way we isolated A and B modules, the quanta modules. Each triangle is split into 6 equal parts by perpendicular bisectors to obtain a final non-symmetrical divisible unit. The result is 120 asymmetrical triangles, 60 positive and 60 negative. The maximum number of equivalent domains on the surface of a sphere, this is the maximum number of equivalent domains on the surface of a sphere. These perpendicular bisectors are the icosahedron's 15 great circles. And then we can see the maximum of 120 equivalent domain is the least common denominator shown in those sketches. Imagine that some number of hypothetical creatures are to inhabit the surface of a large sphere, and it is considered necessary that each one sit in the middle of an identical plot. The consequence of this stipulation is that no more than 120 creatures can fit on the sphere, no matter how large it is. This result is certainly counterintuitive, for assuming that a large enough sphere, it seems that we should be able to accommodate as many creatures as we want. However, The unyielding laws of symmetry limit the population to the unexpectedly low number of 120. If we go back to the 31 great circles diagram to observe the 120 triangles in context, these asymmetrical triangles are true least common denominator units. Any one of them contains all the geometric information necessary to reconstruct the entire pattern. This is an important factor in the development of geodesic dawns, as will be seen in the next chapter, which discusses the relationship of great circles to geodesic dawns.
Okay. Can we stop there?
If you say so.
Yes, that's overdose. But I want to show Lee something for her to see. Are we okay?
I'm watching. I'm watching.
Okay, Lee, you see this? This is, can you pin me? This is the icosahedron.
Yes.
You remember this thing, huh?
Yes.
How many?
You can take it apart.
Yes, how many equilateral triangles does it have? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That is 10 on this where I'm holding. And then we have another 10 here.
Another 10 there. Yes.
Yeah, that's 20 equilateral. Yes.
Yes.
Okay. Now, if you take, just let me get a ruler that is a white color. Yes. You see this guy? Here. Look at this face.
Yes.
Look at my ruler. If I take this, imagine that this is a trace of a circle, of a great circle.
Okay.
Passing by the center. You see
Okay.
that it divides this thing into stuff that has 100, that has 90 degrees in the middle. And I can divide here, I can divide here, I can divide there, I can divide. This will give 120 of those guys.
Ah, okay.
And that's the maximum that you can have.
Mm.
That is transformable. And what are those guys? What are they? The quantum of energy. Quantum of energy.
Oh.
That's fully defined. 1/8 of a tetrahedron. That's what those guys are. It's composed of things like this.
Oh, yes. Yes.
That's the whole thing that she was explaining here. And that this is on the icosahedron. If you do it, you remember that the icosahedron will collapse into the octahedron, huh? in the Jitterbug transformation.
Yes.
Those things that you were cutting were also cutting the octahedron that is inside, isn't it?
Yes. Yes.
Yes. So, but the whole game, as we know it, is coming back to the initial relationship that we have, that we say we have edges and faces. All he's doing is looking at the center of faces and cutting them with something,
Yeah.
with a great circle that goes through the middle, that will form what you call an edge.
Yes.
The trace.
Yeah.
If I have this as a face and I take this to cut it, this line here, that was, remember, our shortest distance between these 2 points.
Yes.
Is the edge.
Yes.
And that edge is where you have the exchange, the relationship. When I say I have a relationship with Lee, my most excellent relationship is when I visit Lee to a house, and then I have that close relationship.
Yes.
If I sit here and I talk to you on the phone and do something, it is a relationship, but it's not
the same.
optimal.
No.
Exactly. That's how we go. That's how I understand this thing. there's a mathematical jargon onto it, but when you have these tools, you can play with them.
Yeah.
Huh? The whole map, and then just say you're a kid will always get to something like this, and then will look and say this is not okay, and looks again, and then it realize that this is not okay. A kid, and then put it like this, and it has the stuff. Any kid will do this.
Yes. My
It's such
6-year-old granddaughter did that to Steve.
yeah, just playing.
Yeah.
So it was just the world started as a game, actually.
Mm.
It was a little game.
Oh wow.
And then we redo. We have this. It doesn't happen. Me, I make an eruption. I create a volcano. Boom. It reduces. It reduces. Huh? My
Okay.
volcano does
Okay.
this change here, and then it does things until it got to where it is, and it will change again.
She found
Right?
that out. She made
Yes.
bracelets out of it.
No, sure. That's what the kid that Richard was talking the other day. It's not constrained. Just plain.
Yeah.
Just plain. So for adults like us that has been conditioned so badly, they say always try to start from the macro, from the widest. Because we too conservative. We lock ourselves by the rules of society, by our upbringing, by whatever that we have into our little corner, and we believe that that is the world. It's not. And not only is it not the world, it is changing all the time. It's part of something that's changing.
It is.
Yeah.
Thank you.
All
I
right.
appreciate that.
So what I would recommend everybody, this thing, unfortunately, this one, when you go onto Google, I don't know. I'm sure Fred can find it in China with Alibaba. We don't find it anymore because when you Google it, it doesn't come out anymore. So get it, and then the magnet.
Doesn't it have a number on it somewhere?
I don't know. I lost it. When I think I don't know who suggested it. Was Susan. We all went and bought it, and then after that it disappeared from the shelves of Google.
Oh.
But it is very useful with the magnets, and then the paper and the scissors, paper, and then our beautiful tools. This one, and then the compass, and that's it. And then we get to play. You should make time to play, though. That's the fuel of the game.
No, I do. Steve
Yeah,
has
you should make
those.
time to play. In your busy schedule, you should really make time. Like just have the child patient. You just be a child again. Be a child again.
I agree.
Yeah, and preferably a little girl.
Thank you.
Rather than the boy, because the boy is scattered. He doesn't have the concentration.
Well, thank you, Manu.
Okay.
Whoops.
Any other comments? All right, then. I think it's time. So, Manu, how are you feeling, and what is your takeaway today?
I'm feeling playful. I'm feeling happy, like a baby. So that's my takeaway. I feel good. I feel happy. Richard, how do you feel? What do you take away?
Oh,
You are mute, Richard. You are mute.
Yeah, I feel good as well. And one of the things that I was doing the jitterbug and the reference to the polars, polar opposite, is visualizing the jitterbug that I have. And I always remember the way you position it, there's a triangle at the very top, and there's a triangle at the bottom. And that you can start to move it in a vertical, or you could move it horizontally. It doesn't matter which way you fix it, but you hold it like you might hold an accordion. And then as you start to push it in, you get the feel of the spin and the torque, and eventually the folding. But if you just get into the rhythm of the accordion, if you want, the two triangles coming in, going out, coming in, going out, then they dance. That's where the jitterbug sort of name comes from, is that you can see this geometric sort of figure dancing as it twists and turns and torques, and doesn't go all the way down into those other shapes because you keep it in that motion form. And so that's part of what I'm taking away, is again this notion of the vertices or the axes that are important in the up and down or the back and forth. And it's what came to me when I first learned about precession and trying to understand what precession meant in terms of being able to have a back and forth movement, that motion that creates a movement that's perpendicular to that motion, to that axis. And that's what came to me when I was struggling with the problem that I had with students who could be in the field trying to learn how to be helpers, and having a relationship with a client was really important. So important that if you failed that part of your course, you failed everything. And I would have students, because I was in the administration, who would come to me and say, my supervisor in the field just fired me, failed me. And so when you said, well, what did you do? Or what evidence did they give you to measure, if you want, your failure? And most often it was their judgment, their subjective judgment that they didn't think you were very good at that. And so I was really struggling with, if that's such a powerful thing that we could actually fail students in everything if they can't meet that one objective. I was trying to say, what are the mechanics of the relationship, this back and forth that's so important? And that's when I realized that it's precession. And that if you can't get into that dance back and forth like the bee does with the flower, you can't then generate motion perpendicular. So you can't generate motion that goes from problem to solution. And so it's very important to understand the mechanics beyond just the subjective feelings. And I guess maybe I was trying to do what Fred was getting at earlier, of how do you measure a relationship, and how do you measure it in a way that says that you're good at creating motion perpendicular to the axis, or you're not, and understand that mechanic. So this helped me continue on that journey of understanding the human dynamic, if you want, from a physical modeling, measuring sort of aspect. So I really appreciate being able to go through this part of the reading again. where do we go now? Lee, how are
Yes.
you feeling, and what's your takeaway?
I'm feeling really good. And I thought of something in your conversation. There is a movie of a professor at a school, a high school, that keeps playing his own, coming up with an opal of his own. He wants to perform this opal. And the students are now beginning to understand what he is trying to do. But he has been given a difficult chore to help a football player or a basketball player, I'm not sure, but a young man who can't even tap his foot in time with music. And he has to make up his points to graduate and go into another class. And he would not graduate, and they would not have him in the team, and he is needed in the team. And so, what did this professor do? He danced, he had different beats, and he put him on to the bass drum of the school band that marched at the games, and he learned a beat by the guy putting a helmet on the head of this boy and hitting him so that he could do the same beat. He just kept pounding on his head. Now he's got a helmet on, and he can hear the beat through and feel the beat. And it taught this young man to have a beat. And so it developed his ability to dance, to do the jitterbug. And it was this ingenious professor who got him to graduate from one class or one grade to another so that he could continue playing in the field that he was they wanted him in athletics. So that is a way for me to understand what you were talking about, Richard, in situations where individuals will not think the same, but they know the same if they're taught. And they have to, and the one has to teach the other how to think the same way. And so in essence, I am learning from all of you how to understand the circles, the tetrahedrons, all of that. I am learning slowly, but I am learning, and I appreciate all of you teaching me a little bit at a time. And I'm hopefully going to be able to join you all next year with a powerful mind. I'm hoping and praying. Now, Fred, how do you feel, and what have you taken from tonight?
Thank you, Lee. So basically what you're saying, Lee, is that we put a helmet on you and we are trying to hammer something into you.
Exactly. You are.
And as you described it, I was wondering, maybe without a helmet it would be faster.
No, that might hurt. That might hurt.
Yeah, but pain pain is a good incentive on many things. So the fact that it hurts is and that it should be avoided is mostly a cultural, that it must be avoided at all costs is a cultural artifact. Sometimes pain has its usefulness.
Well,
I won't delve further on that. What's my takeaway? My takeaway is that it's very interesting to see small groups, and I've seen a few small groups in the past 2 months. When we're in the small groups, I see Lee opening up, and I see Lee smiling, and I see Lee stopping us. Stop right there, you people. I'm not following. I want to have an explanation about the circle and the jitterbug because I'm lost. And I find this extraordinary. I find this very good. That somehow, for some reasons, in a small group, Lee is able to assert herself. Whereas in a larger group, there's something that's happening that makes you take a step back a little bit. And I don't know what it is, but I think I should raise this to Steve's attention and see if he's got an idea about how to make an environment that makes you more able or more willing to open up even when there's more people in the group. It's because I find this wonderful. It's very refreshing. You asking questions that are very essential to be asked, I believe. And so that's my takeaway. My takeaway is that there may be some slight adjustments to make in the dynamics of the group so that you find your voice as you did today. So I very much like that. And how am I feeling? Hungry. I'm feeling hungry. It's time to eat something.
So am I.
Okay, thank you very much, all. Yes.
There's one little thing that I want to say. When you take the vector equilibrium, it has 24 faces.
You've got to hold this for
24
next week.
triangular.
We've got to hold this for next week. We've all done.
No,
we all done.
Just hold. I just want to leave you. Okay. All right.
Hold on to the thoughts, and next week we come back.
Next week. We're both hungry.
Thank you all. Thank you, Richard. Thank you, Lee. Thank you, Manu. Bye-bye.
Thank you all.